Alright, boys and girls, let's learn a little bit more about projectiles. In this video, we're going to cover the more general case of what happens when a projectile is launched at an initial angle. The first thing we need to do is understand that all the big ideas we've learned previously about projectiles are still valid. Namely, that the only force acting on them is their weight, that they move forward at a constant velocity, and that they accelerate downward at g, 9.8 meters per second squared. So a projectile launched at an angle, which might look something like that, with some initial velocity at some angle relative to horizontal, that initial velocity now has both a vertical component as well as a horizontal component. So we're going to first have to resolve into an x component and a y component. After that, our big ideas tell us what to do, along with what we've learned previously about kinematics. So the initial vertical velocity now is not zero like it was previously. So this is the more general case. So if we have a projectile that's launched upwards and forwards, it moves forwards and moves upwards. It's got a constant horizontal velocity. And so our picture would end up looking something like this. Notice that each time it moves forwards by the same amount. So all those spaces are equal because the horizontal velocity is constant. The vertical velocity, however, is changing because of gravity, accelerating downwards. So as we go up, our velocity gets smaller. When we reach the maximum height, it's 0, and then coming back down, it increases again. So we go from a big positive vertical velocity to 0 vertical velocity to a big negative vertical velocity. So if we were to graph the vertical position versus time, now it would be a full parabola, kind of like the shape that it makes on the page, and then the vertical velocity would do something like that. At this point right here, it is at its maximum height. So we need to be able to look at those graphs and determine when it reaches its maximum height. So the first thing we'd have to do when analyzing a projectile launched at an angle is resolve the initial velocity into its horizontal and vertical components. So kind of redrawing the picture would look something like that. So we would break that up into an x component and a y component, and then use our three trig functions. So for example, use the sine to find Vy. So Vy would look something like that. And then you would do something similar with the cosine, since the adjacent side is Vx, to find your horizontal component. So that's always going to be our first move in analyzing a projectile launched at an angle. So let's look at a couple of examples of problems we might be faced with in the near future. Suppose for a second that you kick a soccer ball at a 37-degree angle relative to the horizontal from the ground at about 50 meters per second, which is a ridiculously high velocity for a soccer ball. You're talking like 150 miles an hour, something like that. But let's just suppose, because it gives us nice numbers. So here's our picture. And the first question is, what is the maximum height of the soccer ball? Like, how high does it go? Would it hit the ceiling of the gym you're playing in? I don't know why you're playing soccer in a gym, but let's just pretend. So there's the path of the soccer ball. And then that's the height we're looking for. We're looking for that maximum height. So step one is to resolve the velocity into components. So draw a right triangle. And you can do sine, cosine, or tangent to figure out your components, or you might recognize that that's a 3, 4, 5 right triangle. I'm going to save a little work there. Second step is to write out our givens and our unknowns. Since it's a projectile, I would recommend you do both the horizontal and the vertical motion kind of separate like that. So we got our velocities. We're starting at the ground, so let's make our initial height 0. Why not 0? We're looking for a height, so y would be my question mark. We're accelerating at 10 meters per second squared because it's due to gravity. but we need to remember to make it negative in this situation. Negative because acceleration is in the opposite direction as the initial velocity. So remember, whenever these two things are in opposite directions, they have to have opposite signs, so the easiest thing to do is to make your acceleration negative. And then the other thing that we need to pull out of our brains is that the final velocity when we get to the maximum height is 0. Third thing we should do is figure out an equation to use. Figuring out that we don't really care about the time in this situation would be an important thing to do, because that tells us to use the Vy squared equation. And so the final velocity is 0 going up and down, and then we can solve that for delta y. And then substituting in our numbers, you can see here that it's important to make the acceleration negative because it needs to cancel out with the negative sign that we got in the equation. If you don't, you're going to get some random negative maximum height, like you kicked the soccer ball and it went down through the earth somehow. And so doing the arithmetic, we'd get something like 45 meters. So this soccer ball goes up about 150 feet. Again, it's a little bit fast for a soccer ball. All right, another question. As long as we're dealing with this soccer ball, let's figure out a few things about it. Next question is, how high is it after 2 seconds have passed? So the thing that we need to do here is recognize what hasn't changed and what has changed. So here is our table from the previous page. Just copied it directly from there. Let's talk about the things that have changed real quick. The time is no longer going to be something that we don't know. We're told what the time is right there. So let's change the time to 2 seconds. Now it's not at its maximum height anymore, so we need to change that velocity. Final velocity it's irrelevant. We don't really care what it is. And that helps us figure out to use this equation, the 1/2 at squared. And so substituting in the numbers, because we don't have to do any algebra here, we get something like that. And so 30 times 2 is 60. And then the other part of that is negative 20. So notice here, if you don't include that negative sign, instead of getting the correct answer of 40 meters, you'd get something like 80 meters. Like somehow it went up and sped up, is what you would be essentially doing if you forgot that negative sign. So the negative sign is kind of important. All right, I got one more question here. Now, the next question is, how far away does the soccer ball land? So we're going to play the same game. We're just going to copy down what we did in the previous part and talk about the things that have changed. We're no longer dealing with the time of 2 seconds. X is now our unknown. We're starting at a height of 0 and we end at a height of 0. So both of our y's are 0. And then the final velocity isn't irrelevant anymore. The final velocity is negative 30 meters per second. Mr. Marek, how do we remember that? Well, remember that at any given height, the velocity is going to be the same regardless of whether or not it's going up or down. And so when our two positions are the same, then our velocities should be the same as well. Just one's positive and one's negative. So that's something that has to come from our brain. If we don't remember that, we can still do the problem. It's a lot harder to figure out how long it takes the projectile to reach the ground. Speaking of, remember that time is the important factor that relates the vertical and horizontal motion. So we need to find the time first. I know that if we had the time, then we could find how far away it is by using our constant velocity equation for position. X equals x naught plus v times t. So if we use that equation, it's our very first accelerated motion equation, we can solve that for time if we remember that our final velocity is the opposite of our initial velocity. So if we don't remember this, then we're going to be missing that piece right there, and we're going to have to do something more difficult. So that's a relatively easy set of numbers to crunch. We get something like 6 seconds. And then just plug that into our constant velocity motion equation. And we get something like 240 meters. which again is a ridiculously long way away to kick a soccer ball, basically 2.5 fields, because our velocity was ridiculously big. But it gave us easy numbers to work with. That's why we did a ridiculously large velocity. Alright, so here's a checklist to follow. And I've kind of written these in order of importance. Like, what should you focus on and worry about the most? The first thing we need to be able to do is describe, meaning words, graphs, diagrams, 3x diagrams, what have you, projectile motion. When is it going up? When is it going down? When is the velocity constant? When is it changing? Can we graph position versus time in both directions, etc., etc. Second important thing is, can we explain why projectiles move the way that they do? And pro tip, that would be in terms of forces. Forces are why things move the way they do. Third thing is being able to solve problems involving horizontally launched projectiles. So if you were to have a quiz or something like that in the near future, the problems that you would see would most likely involve mainly horizontally launched projectiles. And then the last thing would be to solve problems involving projectiles that are launched at an angle. Kind of the three examples that we just went through. So in the near future, you might have a few like that you'll be asked to do. So that's all for this projectile video. We'll be working on this a little bit more, so we'll get some practice at it. And I will see you next time in class. Ta-ta.